Today we are going to discuss another application of our isomorphism extension theorem. Here what we are going to do is let E be a finite extension of a field F. And sigma is an isomorphism from F to F prime. F prime is a different field. So then the number of extensions of sigma to number of extensions of sigma to an isomorphism from E to a subfield of F prime closure is finite and is independent of sigma F prime and F prime closure. That implies number of extensions depends only on E and F. What I'm trying to say is F is a field and we have a isomorphism F prime, and there is a finite extension, meaning it's an algebraic extension also. Then the number of extensions going out of E is independent of this F closure, F prime and F prime closure, and even the sigma. Meaning if you take any sigmas, say sigma 1, sigma 2, any sigmas from F to F prime, if one of them has n extensions, then every sigmas will have the same number of extensions. Doesn't matter how the sigma behaves on F. And the theorem also says it is not depending on even F prime. It can go to any field still the number is same, meaning that number depends only on the dimension of E over F. So that is what the theorem says. It is actually going to depend on our isomorphism extension theorem. So what we will do is we have two parts. The first part says that doesn't depend on sigma. So let us start with what we'll do is we'll start with two different isomorphism from two different fields from F. F2. We don't know, these are two different fields, and this is actually, this is sigma 2 and this is sigma 1. Two different isomorphism. Sigma 1 and sigma 2 are isomorphism from F2, F1 and F2 respectively. Then sigma inverse, sigma 1 inverse, sigma 2 after sigma 1 inverse is an isomorphism from F1 to F2. We are assuming that this is onto, otherwise take this as sigma 1 of F. But this is an isomorphism. Is an isomorphism from F1 to F2. So naturally, we can talk about an extension from F1 prime to F2 prime. Sorry, F1 closure to F2 closure. Because F1 closure is an algebraic extension of F1, and this is an isomorphism from F1 closure to F2 closure. So this is an extension of that. So this is lambda. What I'm trying to say here is, when you apply lambda to an element in F, it is same as sigma 2 after sigma 1 inverse of that element. And we have an E somewhere here. E is a finite extension of F. And sigma 1 is an isomorphism from F to F1. So we can talk about an extension here. Tau 1 is an extension of sigma 1 to a subfield of F1 prime. Now, the thing we are going to prove is, for every extension tau 1 of sigma 1, there is an extension for sigma 2 from E, meaning there is a one-to-one correspondence between the extensions of isomorphisms. So here, now what you do is, let alpha belongs to F. So what is tau 1 alpha? Is equal to sigma 1 of alpha, because alpha tau 1 is an extension of sigma 1. Now, what is lambda of tau 1 tau 1 is taken from E. So this is actually going to be sigma 1 of alpha, because alpha is coming from F. Then this is actually what? This is actually an extension of lambda is an extension of sigma 2 after sigma 1 inverse. So you can write it as sigma 2 sigma 1 inverse. This is this, and this is going to be this, just because alpha is coming from F. And what is this? This is actually sigma 2 of alpha. What does that mean? That means lambda after tau 1, lambda after tau 1 is an extension of lambda sigma 2, because if you take any element from F, this is this isomorphism is mapping to the same element as W2 maps, sorry, sigma 2 maps. That means for every tau 1, that is an extension of sigma 1, there is an extension for sigma 2 from E. So similar argument, you can say this is going to be tau 1 of tau 2 of lambda inverse is an extension of, similarly, extension of sigma 1. So that means for every tau 2, but means extension of sigma 2, there is an extension for sigma 1 from E. And that implies the number of extension of any isomorphism from F are same, and is independent of the isomorphism and F prime and F prime closure. Now we need to show that that number is finite. That actually comes directly from the fact that E is a finite extension of F. So E is a finite extension of F, implies E is equal to F of alpha 1, alpha 2, alpha n for some alpha 1, alpha 2 dash dash alpha n in E. That's the definition of finite extension. So each extension of any isomorphism from F should map each alpha I to its conjugate. Because otherwise it won't be an isomorphism. Any extension. Okay. Now let degree of, see these alpha 1, alpha n, alpha 1, alpha 2, etc. alpha n are algebraic over F. So degree of alpha I comma F is equal to Ni. That implies each of the extension of an isomorphism from F should map alpha I to one of its Ni conjugates. So the total number of extensions of any isomorphism cannot exceed Ni times n. That means the number of extensions of any isomorphism from F is finite. So what we have proved is if E is a finite extension of F, then the number of extensions of a isomorphism from F to a field F prime is independent of the isomorphism and F prime and F prime closure. It depends only on E and F. So what is happening here is F to F prime, this is E, this is sigma, then you are getting an extension here, tau of, so there is an F prime here, F prime closure here, this is tau of, sorry, this is just tau, and this will be tau of E. This is a subfield of F prime closure. The number of taus does not depend on sigma. it is an extension of sigma, but the number of toes is depend only on E and F. It doesn't depend on sigma, F prime or F bar. When you say toe is an extension of sigma, toe is an extension of sigma implies toe of alpha is equal to sigma of alpha for all alpha in F. So instead of saying this, let us convert into another situation. Let's take F to F identity map. And there is an extension here. And toe is an extension of I. This is our I. To a subfield of F closure. Both are F. So then here also what we can say that the number of toes, T's, the number of extensions of I depends only on E and F. And what does this toe do here? Toe leaves, or toe is an isomorphism that leaves F fixed. It is same as saying that toe is an extension of I. So we can reorder, or you can reframe this theorem to a definition. Definition is if E is a finite extension of F, then the number of isomorphism from E to a subfield of F closure, leaving F fixed, is called the index. Index of E over F, and is denoted by E over curly brackets. Leaving F fixed, that is actually replacing the extension of the identity map. We already proved this number does not depend on the image of the isomorphism, and not even the isomorphism. So we have another definition. It's called index of E over F. We have a similar definition with a square bracket. This is the dimension of E over F when E is considered as a vector space over F. this is the number of isomorphism from E to a subfield of F closure leaving F fixed. I'm going to derive a relation between the indexes of finite extensions. We have the similar results in terms of degrees. If E is a finite extension of F and K is a finite extension of E, then the degree of K over F is equal to the degree of K over E times the degree of K over F. This is in degrees. So we are going to find out a relation in terms of indexes. So let E is an extension, finite extension of F, and which is K, and K is a finite extension of E, where K and E are finite extensions. Then let S1 is equal to the isomorphism from E to a subfield of F closure leaving F fixed. And S2 be the isomorphisms from K to a subfield of E closure leaving E fixed. And S3 be the collection of all isomorphisms from K to a subfield of F closure leaving F fixed. And this implies S1 is equal to the index of E over F. This implies the cardinality of S2 is equal to K over E. And this implies cardinality of S3 is equal to K over F. So every element in S2 is an extension of an element in S1. And these extensions forms the elements in S3. That means cardinality of S3 is equal to cardinality of S2 times cardinality of S1. And that implies K over F is equal to K over E times E over F. So we are having the same kind of result as in degrees.